All right, if you're a physics student, you've probably heard horror stories about the Irodov problem book. Well, today we're jumping headfirst into one of its classic challenges, problem 1.70. So let's get this thing solved together.
So what's the puzzle we're trying to solve? Imagine this. You've got a bar and a motor just sitting on a surface. There's a string connecting them. Suddenly, the motor whirs to life and starts reeling in that string, pulling them toward each other. The big question is, with friction fighting them every step of the way, how long does it take before, well, they collide?
Okay, let's get into the nitty-gritty, the actual problem statement. We have a bar and a motor on a flat, horizontal surface. We know there's friction, and they give us the coefficient K. A thread connects them, and the motor starts winding it up. Now here's the crucial info. The bar is twice as heavy as the motor. And, this is really important, we're told the bar moves with a constant, known acceleration, which we'll call W. Our one and only goal is to find the collision time.
Before we write a single equation, the best first step is always to get organized. What do we actually know? We've got the starting distance, L, the bar's acceleration, W, the friction coefficient, K, and the fact that the bar's mass is double the motor's. And what are we trying to find? Just one thing, the time t until they collide. Laying it out like this just makes everything so much clearer from the start.
Okay, our info is all sorted out. Now comes, without a doubt, the most important part of any dynamics problem. Seriously, if you mess this step up, everything else that follows will be wrong. We have to figure out all the forces. And the only way to do that properly is with free body diagrams. We're going to draw one for each object to really see what's going on. Now, you might be tempted to look at the whole system at once, but trust me, that's a recipe for confusion. The trick is to keep it simple. We're going to look at the bar all by itself, and then we'll look at the motor all by itself, one at a time. This methodical approach is going to save us a lot of headaches. Okay, let's focus on the bar first. What's acting on it? In the up and down direction, it's pretty straightforward, right? You've got gravity pulling it down, and the normal force from the surface pushing right back up. They cancel each other out. The interesting stuff is happening horizontally. You have the tension in the string pulling the bar towards the motor, and fighting against that pull, you have friction, which always opposes the motion. Bar is done. Now let's switch gears and look at the motor. Vertically, exact same story. Gravity down, normal force up, nothing's happening there. But horizontally, here's where you need to be careful. That same string is pulling on the motor, but which way? It's pulling it towards the bar. And just like before, friction is dragging its heels, opposing the motor's movement. Let's just pause on this idea of tension for a second, because it's so important. Did you notice how it pulls the bar towards the motor, and it pulls the motor towards the bar? It's a two-way street. That's a classic action-reaction pair, Newton's third law right there. The magnitude of that pulling force, T, is the same on both objects. It's the internal force that's bringing this whole system together. Okay, we've got our force diagrams, we've visualized everything, the physics picture is complete. Now it's time to translate these pictures into the language of math. And what's our tool for that? Good old Newton's second law. Yep, F equals ma. We're going to apply it to the bar, and then we're going to apply it to the motor. So let's start with the bar again. We only care about the horizontal motion. What's the sum of the forces? We have tension, T, pulling it forward, and we have friction, F bar, pulling it backward. So the net force is T minus F bar. And according to Newton, that has to equal the bar's mass, which the problem tells us is 2m, times its acceleration, which we were given as W. But wait, we can get more specific. We have a formula for the force of friction, don't we? It's just the coefficient K times the normal force. For the bar, the normal force is equal to its weight, which is 2mg. So let's just swap out F bar with K times 2mg. And there we go. We now have our complete equation for the bar. All right, now it's the motor's turn. Same process. Net force equals mass times acceleration. The forward force is tension, T. The backward force is its own friction, F motor. So T minus F motor equals its mass, M, times its acceleration. Now listen up, because it's a huge trap that so many students fall into. We have to call its acceleration something new, like A motor. We absolutely cannot assume it's the same Y as the bar. We don't know that yet. We have to find it. And just like we did for the bar, we'll plug in the real value for the motor's friction. It's K times its normal force, which is just kmg. So look at what we've built. It's actually pretty cool. We have two clean equations, and if you count them up, we have two things we don't know, the tension, T, and the motor's acceleration, A motor. Two equations, two unknowns. This is a solvable system. We're in business. So what's our game plan? Let's look closely at that first equation, the one for a bar. We know everything in it, except for tension. That's our key. We can use that equation to solve for T. And once we have a value for T, we can just plug it right into the second equation for the motor. That'll let us solve for the one thing we need, the motor's acceleration.
All right, let's do a little algebra. From that first equation, we just move the friction term over to the other side, and we find that tension is 2m times the whole quantity W plus kg. Simple enough. Now, we take this whole expression for T and substitute it into our second equation. And watch this. This is pretty neat. Every single term has a little m in it, so they all cancel out. A little bit of cleanup, and we're left with a nice, clean expression for the motor's acceleration. It's just 2w plus kg. And take a deep breath. The hard part, the dynamics, the forces, it's over. We figured out how fast both objects are speeding up. Now we just have to switch hats and think about kinematics. All we need to do is use these accelerations to find out how long it takes for them to cover that initial distance L and meet in the middle.
Now, you could try to track the position of the bar and the position of the motor and see when they're equal, but honestly, that's the long way. There's a much smarter, more elegant shortcut, thinking in terms of relative motion. Instead of two separate objects, let's just think about how quickly the gap between them is closing. Since they're accelerating towards each other, we can just add their accelerations. So we take the bar's W and add the motor's 2w plus kg. That gives us a total relative acceleration of 3w plus kg. This simplifies the whole problem down to one number. And because we use that relative acceleration trick, the next step is incredibly simple. The entire situation now just looks like a single thing needing to cover a distance L, starting from a dead stop with this one combined acceleration we just found. And for that, we can pull out our trusty kinematic equation. Distance equals 1/2 at squared. All that's left is to do the final bit of algebra to solve for t. We multiply both sides by 2, divide by our relative acceleration, and then take the square root of the whole thing. And there it is. The time to collision is the square root of 2 times L, all divided by the quantity 3w plus kd. That's our answer. We've solved it. Getting the right answer is great, but to really become a better problem solver, you have to reflect on the why and the common pitfalls. So let's not just move on. Let's think about what this problem really teaches us. I've seen so many people stumble on problems just like this one. Here are the classic traps to watch out for. Number 1, not drawing separate diagrams. It's a recipe for confusion. Number 2, getting tension wrong. Just remember, a rope can only pull. Number 3, forgetting that friction acts on both bodies, and as we saw, using the relative motion trick saves a ton of work. Finally, the big one, assuming the motor's acceleration was the same as the bar's. We had to calculate it, and that was the key. Here's a great habit for any physicist. Do a sanity check. Ask yourself, does my answer make sense? Let's test it in a simpler case. What if there was no friction at all? If we set k equal to 0 in our formula, the kg term just vanishes. The time becomes the square root of 2L over 3W. This makes perfect sense. Less resistance should mean a faster collision, and our formula shows that. It holds up. And that's our breakdown of Irodov 1.70. But don't let the learning stop here. To really master these concepts, think about this. What if the thread wasn't horizontal? What if it pulled the bar at a slight upward angle? How would that change the normal force? And if the normal force changes, what would that do to the friction and to the final answer? Pondering these kinds of changes is how you build true physical intuition. Thanks for working through this one with me.